As we are all familiar, probably in this room, there is extensive planned upcoming exploration of the region near the south pole of the moon. So, an excellent question to ask at this period of time is, what role did basin-forming impacts have on the near-surface structure in the lunar highlands in the region near the south pole? So, we are going to use radar data, specifically Earth-based Arecibo data at P-band, or 70 centimeter wavelengths, because this wavelength can probe the upper tens of meters in the lunar highlands. And so, sorry, I can't really see the screen over here. In a previous P-band study by Tommy Thompson and others in 2009, they found that there were radar variations in the region near Maurolycus crater, which you can see that. It's the red arrow here, just east of Tycho. And they found, or they argued, that these radar variations indicated variations in the megaregolith thickness from SPA basin. So we're going to re-examine this region using these newly reprocessed 70 centimeter Arecibo radar data. A quick plug for these data that Bruce Campbell and I have worked on reprocessing. This is data that are currently online in the PDS, but they also include some additional data that were taken after those data were put online. These were reprocessed using this new autofocusing technique that yields a better SNR, a better spatial resolution, and have been ground truthed to a WAC global mosaic. So they're great. If anyone's interested in using them, we did put them up on Figshare. You can't click on that link, so if you want them, you can either search it and go to the Figshare, or just let me know. I can send you a link to those data. So the region that we're looking at is this region near Maurolycus crater, which again is that crater at the top center of these images. On the left, there's a map of the SCP, the same sense circular polarization. The map on the right is CPR, or circular polarization ratio. And what you can see from the map of SCP and CPR as well is that there are these broad regions of variations in radar backscatter. So there's lower radar backscatter that's a little darker, and then this sort of circular region of elevated backscatter, and then lower scatter again. My scale bars got cut off, but the variation is about 3 dB in the brighter and darker regions. So that's about a factor of 2 difference in radar backscattered power. So there's a pretty good variation in the circular region, which happens to coincide with this broad topographic depression, which has been mapped potentially as a basin. It was mapped as the Mutis Block Basin. It's been debated whether that's an impact basin. If it's not a basin, it's still a topographic depression. So it's still interesting to know about. So the first question we could ask here is, what's causing this broad variation in the radar backscatter that we're seeing in this darker band, this brighter circular band, and then this dark band again? So in radar, we can generally credit this to 2 processes. One could be the presence of a buried lava flow under this higher backscatter region. We call that cryptomare. The other explanation could be that there's some heterogeneous distribution of basin ejecta deposits in this area, with variations in either rock abundance or rock size or difference in composition that leads to variations in the attenuation of the radar signal, so different loss properties. I just don't have enough time to talk about cryptomare. There is more to say here, so feel free to ask me about it, but we're just going to talk about the role of basin ejecta and heterogeneity of basin ejecta contributions in this region. So the Maurolycus region is where this big yellow arrow is. This region probably received 1 to 2 kilometers of ejecta from the SPA basin. So that's a huge contribution from SPA. And then what I did was just calculate all of the other major impact basins that would have deposited at least 1 meter of ejecta or at least 10 meters of ejecta to this region. And there are 10 basins after SPA that deposited 10 meters or more of ejecta in this region. And then another 5 to 10 more basins that could have contributed more than a meter. So we can say to a first order, this region has been extensively modified by basin ejecta. But just to take a very sort of superficial approach, we're talking about the upper few tens of meters. Let's look at the most recent basin, which is Oriental. So I apologize for this color stretch. It made me feel a little insane when I look at it for too long. But purple is darker, so lower backscatter, and then red and yellow is brighter, so higher backscatter. The boxed area is that more Lycus region with, you can't really see that, with lower backscatter, and then this higher backscatter region in the middle. What we can see from this spatial projection and the other radar swaths is that that elevated backscatter region extends westward and actually contains some sort of linear elevated backscatter ray-like features that all point back towards Oriental Basin. So it's not crazy to think that maybe this elevated backscatter region that we're seeing here is just a more extensive distal Oriental ejecta deposit that made its way all the way to this region here. And maybe because the presence of this mutus block basin or not basin, maybe that basin ejecta just got concentrated into this topographic depression and is a relatively thicker layer in this area. There is some evidence to support this in that in Jacobi crater, right in the middle of this area, there's a small outlying exposure of the Hevelius formation, which is an Oriental ejecta sculpted unit. So we know that there is a surface expression of Oriental ejecta secondaries, but if there's Oriental material on the surface, maybe it's not crazy to think that there's Oriental ejecta in the near surface. So that could be explaining the broad radar backscatter variations that we're seeing. I did mention at the beginning of the talk that there was this previous study by Tommy Thompson arguing for SPA megaregolith. And in that study, they looked at the distribution of radar bright craters, RBCs. And that's these circles in this plot on the right. They found that there's a decreased abundance of these RBCs south of a boundary at 48 latitude, 48 south. And so they argued that this is evidence of a thickening wedge of SPA megaregolith as you get closer to the basin, right? So as in the converse, as you get farther from SPA, the megaregolith wedge thins, and you get more blocky radar bright craters as you get farther from the basin. So what we did is we remapped the distribution of these radar bright craters in the reprocessed Arecibo data. That's all these green circles over here. And there is still that apparent boundary at 48 or 50 degrees south, where there's more radar bright craters above it, and there's fewer to the south, although there are still a few. But there is kind of this nice correlation in our broad radar bright area and an absence of radar bright craters. So let's see. So what this indicates, if you put all this together, is that the radar bright crater distribution does indicate that the megaregolith, arguably from SPA, is thinning towards the north. But what we can see here is that the distribution of the radar bright craters is not one-to-one in our putative Oriental ejecta concentration here. You have a few radar bright craters in the eastern portion of this radar bright area. So maybe what you have is you have thinning SPA megaregolith to the north and thinning Oriental ejecta as you go to the east. And then these few radar bright craters in the broadly radar bright region are locations where you're actually punching through that Oriental distal ejecta, probing the blockier SPA megaregolith that is itself thinning to the north. So basically the takeaway here is that the heterogeneous radar properties of the region implicates a very complex and changeable stratigraphy from the very simplest stratigraphic knowledge of this region, where you have the youngest basin Oriental and the oldest basin SPA. There, as we showed in that table a few slides ago, there's like 15 other basins in between. So really just want to drive home that the highland stratigraphy is really complex. So the last thing that I want to quickly cover is why the Oriental ejecta is generally brighter in this region than the surrounding highlands materials. This could generally be that there's more blocks in the near surface, or there's some compositional distinction. The fact that we don't see any radar bright craters in what would be the thickest part of this potential Oriental ejecta suggests that it's not that this is blockier, which does suggest that maybe there's some compositional distinction in the area, meaning that maybe the Oriental source material has different loss properties than the surrounding highlands. I'm going to have to skip the nuance of this slide because I'm basically out of time, but I'll just say that we do know that the presence of the mineral ilmenite attenuates the radar signal much more efficiently. But just from looking at the mare, where we have a pretty good knowledge of where there are several weight percent variations of titanium, that's not the only thing that controls the attenuation of the radar wave. And we know that there is very little ilmenite in the highlands. So there are obviously secondary components to radar wave attenuation, and we don't know what they are. We don't know what they are in the mare, and we have like no idea for the highlands. So I don't know what the compositional variation could be, but this could be a cool place to investigate some sort of secondary radar attenuation signal. So the takeaway is that the highlands are really complex. There's been a lot of basin ejecta layering. And looking forward to exploration, there was a GPR that was selected to go on the LRV. So that could be a great way to distinguish between these kinds of questions about rock abundance and composition using radar. Thank you.